Welcome back to multivariate calculus. In this video, we're going to be continuing our review of plane analytic geometry with a discussion of second-degree equations. You should be familiar with some second-degree equations already. The parabola is the classic second-degree equation. A circle is another second-degree equation. The others are the ellipse and the hyperbola. Depending on the courses that you've taken previous to this point, you may or may not have spent much, if any, time looking at second-degree equations. There are a ton of different things that you can do with equations in these forms. There's a lot beyond what I'm going to really worry about. So for this video, if you've not seen too much of second-degree equations before, it shouldn't be too hard for you to catch up with. And if you have seen them before, this should serve as a quick refresher of the basic tools that we're going to be working with. All right, so without any further ado, let me get my head out of the way. In general, a second-degree equation in two variables is any equation which can be written in the form ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. Anytime you can write an equation in that form, you get a second-degree equation. There are a ton of parameters here. The first thing I want to mention is that there's actually too many parameters. The value of f doesn't need to affect anything. As you'll see as we go through this, very often we're going to just divide through the equation by f so that f is -1. And then just every other parameter is scaled based on that. It makes life a little bit easier. It makes things a little bit more consistent. But because you can multiply both sides of an equation by whatever you want, you actually don't need that many constants. These two parameters, d and e, are used for translation. They will shift the graph. D will shift the graph left and right. E will shift the graph up and down. Not directly. It's not a one-to-one thing. You have to do some work to get there. But for the sake of convenience, I want to specifically look at second-degree equations whose graph is centered at the origin. So we're going to set d equal to 0, and we're going to set e equal to 0. The parameter b here is used in handling rotations. For example, I mentioned that an ellipse is a common second-degree equation graph. You can have an ellipse that is kind of stretched horizontally. You can have an ellipse that's kind of stretched vertically. You can also have an ellipse that is stretched on some other kind of weird angle. Once again, for our purposes, I'm not going to worry too much about that because we're going to just simply choose coordinate systems where that doesn't happen. So I'm also going to just always set b equal to 0. Again, in practical situations in the real world, that's not always going to happen. Um, Depending on what you're doing, sometimes it is not possible for that to actually occur. But setting b, d, and e all equal to 0 means that we are going to not have anything rotate. We're not going to have anything shift around. It makes the analysis easier. And so we can focus on the interesting bits. That leaves us with A and C. A and C are both scaling factors. The larger those values, actually, contradictorily, the larger those values, the smaller the curve, and the smaller those values, the larger the curve. But with those ideas in your back pocket, we can start talking a little bit about the specific conic sections. If we set x squared plus y squared equals r squared, so in this case, we have a and c equal to each other, and we actually divide by whatever that is. We move f over to the right-hand side of the equation, and we hope that that comes out as a positive value. Right? Why do we write this as r squared? I mean, first of all, it's the radius of the circle, so it's a useful value for us. But more importantly than that, it stresses r is a real number, so r squared must be a positive number. And that is important to us because if the right-hand side here happens to be a negative number, then there's no solution. Right. Two other graphs. These ones actually don't quite follow the rules that I set out, but it should make some sense to you. X squared equals y squared equals x. These are our parabolas. And I suppose that there should be a constant thrown in to the mix here. Traditionally, it goes right there and is a value 4 times k. And k gives the eccentricity of the parabola. If you have k as positive, you can get parabolas that open upward or to the right. If you have k as negative, you get parabolas that open downward or to the left. The thing that I'm really interested in is the ellipse. Where we have a and b both have to be positive real numbers, but not equal to each other. And then x squared over a squared plus y squared over b squared equals 1 gives you the equation of an ellipse. Interesting points of this ellipse are going to be things like It goes through the points A0 and minus A0. It goes through the point 0b and 0, negative b. And those are going to be the four most extreme values of the ellipse, as you can very clearly see from my beautifully drawn graph here. So for example, if I ask you to graph the ellipse x squared over 16 plus y squared over 25 equals 1, you can get pretty quickly that a is 4, plus 4 squared is 16. You get that b is 5 because 5 squared is 25. So you sketch out some coordinate axes. You plot the point. Since a is 4, that means that x intercepts are at 4 and at negative 4. Since b is 5, that means that the y-intercepts are at 5 and at negative 5. And then we do our best to draw something that looks like a smooth curve and not like an egg. If we fail, we fail. That's okay, but that gives us the basic idea of it. In order to make a little bit more sense of the graph that we're looking at here, we can use computer software to sketch the graph for us instead. So let me go ahead and switch my view over here to Geogebra. Geogebra.org/calculator is the URL that I'm on here. If you've had me in a previous class, we've used Desmos for graphing things, and Desmos is quite honestly a more useful and a more pleasant to use graphing tool than Geogebra. But Geogebra has the advantage of it will also allow us to graph things in 3 dimensions. So it's worth coming over here and getting accustomed to how the 2-dimensional graphs work. So we type in our equation. It looks a little bit ugly, but you can see that equation 1 is x squared divided by 16 plus y squared divided by 25 is equal to 1. You can see that the graph looks incredibly similar to the one that we drew by hand. And you can see that the x and y intercepts have been highlighted here. And if we bring our mouse over to them, we can click and it is happy to tell us at least the decimal approximation of each of those points. Sorry, that second y-intercept falls off the screen a little bit, but you get the idea. So with the software available that can perform this well, I guess the natural question is, what do we care? And so I want to be a little bit specific about that. I want you to be able to look at an equation. I want you to be able to recognize that the equation you are looking at is a second-degree equation, and I want you to be able to recognize whether it is a circle, a parabola, an ellipse, or the next guy we're going to be talking about, a hyperbola. If you can graph it from there, fantastic, but that's not really as important. Having some idea of where the constraints are, what the domain and range of the graph look like is going to be very valuable to us in what we're trying to do moving forward. But just being able to recognize the kind of graph it is and being able to find computer software that will plot the graph once you've gotten that far is going to be a long way towards what I'm looking for out of you in this course. All right, let's go back over to our notes and let's take a look at the one last kind of graph that I said we needed to talk about. And those are hyperbolas. There are, in fact, two different hyperbolas. And the hyperbola simply takes the ellipse and makes one of the terms negative. And there's specific meanings to A and B in a hyperbola that you don't get in an ellipse, so it's a little bit more important which one is which. But again, for our purposes, that doesn't really matter. When x is positive and y is negative, as we see in this first equation, you're going to end up with a hyperbola that opens to the left and to the right. Because if you set x equal to 0, there is no value of y that will ever work. But if you set y equal to 0, and then x equals a, or x equals the opposite of a, will both satisfy the equation. So the points of interest here are at a0 and at the opposite of a0. And then the second one is going to be a hyperbola that opens upward, and that's really bad, and downward. And here, those extents are going to be the points b0 and opposite of b0. So if I'm looking at an equation like x squared minus 2y squared equals 6, first thing I want you to do looking at this equation is recognize that it is a second degree equation in two variables. Then the next thing that I recognize on this equation is that my x squared is positive, my y squared is negative. So it's going to be a hyperbola, right? Different signs means hyperbola. And then you have to be a little bit careful because things can get really messed up if that guy over there is negative. That's not the case here, so nothing to worry about. So I know that this is going to be a hyperbola that kind of opens that way. And I could figure out what those constraints are if I needed to. And in fact, I'm going to come back here and figure out the exact values. But before I do that, I'm going to switch back over to Geogebra, and I'm going to go ahead and get rid of the equation that we've just graphed here and put in a new one. X squared minus 2y squared equals 6. And whoops, type that right into the exponent. All right, so I graph that, I get my hyperbola. And again, you can see that there are two x-intercepts. And in this case, they have horrible, ugly decimal approximations. I don't like horrible, ugly decimal approximations. I want exact values. So it is important that I know where those things come from in the equation, so that if I go back to my notes, I can figure out their exact values. But for our purposes right now, being able to look at the graph, being able to draw the graph is kind of important. Before I wrap up on this, I want to slide my viewpoint over here. You can see that there's some tools on the left-hand side that I had been cutting off because they don't really come up. They're not all that useful in most of what we want to do. But there's a nice hamburger button on the top left of the screen. And if you click that, it brings up a menu, which includes the option to export the image. And once again, it's a little bit off the screen. I apologize. But down at the bottom of the screen right now, actually, let me change my crop once more. There we go. If I eventually zoom out enough, you can see that there's a nice download button. And at least in my web browser, as soon as I click the download button, it immediately starts downloading the file. So that I have it to work with from there. So again, very nice tool, but it does leave a little bit to be desired, very specifically that it gave those two intercept points as approximations, and for what we are doing, we need them to be exact values. So we rearrange the equation. X squared minus 2y equals 6. If I divide both sides of the equation by 6, then I get that our value of a is plus or minus the square root of 6, which means that those points must be at square root 6, 0, and negative square root 6, 0. Right, so exact values are what we're looking for in this course. That's something that shouldn't come as a shock to you at this point in your study of calculus, but it is something that I need to stress. With all of those ideas in mind, here's a problem for you to try. Use Geogebra or similar software to graph the equation x squared plus 10 equals 5y squared. And find the exact coordinates of the axis intercepts. Right? As always, take a few minutes, play around with that one, graph the equation using computer software, and then use algebraic manipulation to find the exact coordinates of the intercepts, x, y, or possibly both. Excuse me. Might be nice to classify what kind of graph it is. It is a second order or second degree equation, not a shock in the lesson on second degree equations, but tell me if it's a circle, parabola, ellipse, or hyperbola, and then find the intercepts. Right? See what you can do on that one, and I'll see you in the next video.